Hey everyone, if you're just arriving, please go ahead and get settled in. We are getting ready to start. Clap once if you can hear me. All right, that's all I'm gonna do. All right, we are gonna turn it over to my colleague Sarah Arena from Biomedical Engineering.
All right, hi everybody, how you doing? Good, good. I know it was a rough weekend. The game started out good, right? How many had their first Enter Sandman this weekend? Yes, awesome, okay. All right, so I am Dr. Sarah Arena. I am the Associate Department Head for Curriculum and Course Coordination within Biomedical Engineering and Mechanics. I'm also a collegiate professor, so I teach a lot of our our sophomore courses as well as some upper level technical electives. So you will probably see me if you come into BME. I'm gonna put this down because I'm short. One of the biggest questions that we get is what exactly is biomedical engineering? A lot of people don't really kind of understand what that is even before they get to Virginia Tech. So essentially what biomedical engineering is applying engineering analysis and design to improve health in some way. So that can go across a lot of different scales, and we can offer all that here within our program. So it can go all the way down to the very tiny molecular cellular level. So we have some faculty who are looking at how you can manipulate or how do proteins cause certain diseases like cancer or Alzheimer's, all the way to a organ level, so looking at how artificial organs can grow vascular tissues to be able to increase their perfusion and things like that. We also have the macro scale, so how many people here know about our helmet lab and the 5-star rating? Yes. If you ever get a chance to tour that facility, definitely do. There's a lot of fun testing that they can demo right there for you. But it goes all the way up to that scale, as well as my research areas looking at biomechanics of human movement. How can we rehab from an injury? How can we prevent injury? And how can we teach ourselves to move in a different way? So biomedical engineering at Virginia Tech covers a wide span. So I said it goes from the tiny scale all the way up to the big scale. These are some of the different research areas that you would have access to as an undergraduate from our faculty. So that includes biomechanics, biomedical imaging, translational cancer research, which just means going from bench to bedside, neuroengineering, biomaterials, tissue engineering, and regenerative medicine. So that probably makes you a little confused that, well, biomedical engineering is very, very broad, and there's a lot of different options that you can do. But our goal is to help you find the mountaintop that is the best for you. So this is actually the Blue Ridge Mountains. Even if you take a couple of different hops along the way, we'll make sure you get to the one that you should be at. So how does our program work? We emphasize hands-on experiences. So we have a lot of hands-on labs that are throughout the curriculum. So this one, within Intro to Biomedical Engineering, BMES 2104, we have you take apart a medical device and try to recreate it, parts of it in CAD, right out of the bat. We also have BMES 3024, which is a cell engineering lab. So everyone gets to have some experience trying to see or work on their pipetting skills and work on culturing cells. As well as we have BMES 3034, Bioinstrumentation Lab. So this is where you're working hands-on with circuitry. Oops, there's that one. We also have a lot of hands-on options within our technical electives. So this is actually a class that I teach, Biomechanics of Human Movement, where you're looking at how the body moves, how we can measure all the forces and everything acting on it, and again, looking at towards injury prevention or injury rehabilitation. We also have a lot of options. For example, this is an immersion course where students got to go to up to Roanoke to be able to play around in the Sim Center, which is a place where doctors actually go and train. This is a training tool for laparoscopic surgery. So we really want to emphasize that hands-on experience for you so that you're ready once you graduate to go out and do what you want to do. We also have a very unique focus on fundamental engineering principles. This allows you to really apply them to the 21 credits of technical electives that you have. And we'll talk about those in a second. But those 21 credits give you flexibility to tailor your degree to what you want to do. So those that are interested in cell and tissue engineering will choose very different elective options compared to those that are more interested in biomechanics or biomedical devices. So majoring in biomedical engineering is a total of 124 credits. Within that includes 21 technical elective credits that let you specialize the curriculum to your areas of interest. And to help you pick your electives, we kind of created 3 bins, or 3 categories, which is biomechanics, biomedical devices and imaging, and cell and tissue and engineering. So we have a list of all of our elective options and kind of help you guide you to which one's kind of more aligned with the area that you might be interested in. What's also great is that if you start out in one area and you don't like it, you can definitely pivot to another one and complete the rest of your elective credits in that one. In terms of experiential learning, I know we have a lot going on that slide, but a lot of our students complete undergraduate research. Over 60% of our students complete undergraduate research towards their degree requirements. We allow 3 electives on undergraduate research to count towards your 21 technical elective credits. We also have over half of our students completing internships and co-ops, which is a really great number, and they're doing them at these really large medical device companies. We also offer design sprints, so these are within the curriculum as well as outside the curriculum. So one of the pictures in the very center that you can see, J-Labs, is actually a design sprint that we were able to have with the incubator for Johnson & Johnson up in Washington, D.C. We also offer a lot of clinical immersion. So one of our classes, BMES 3004, or no, sorry, that's helmet design. 3114, there we go. Needs identification in healthcare allows you to go into several clinical settings around Southwest Virginia to be able to identify needs within specifically a rural community and be able to take that towards, say, an undergraduate research project or your senior design project or what have you. So far from our first couple of cohorts that graduated, over 80% have done either undergraduate research or an internship or co-op before they've graduated. For advising in BME, we have an amazing academic advisor. She is right down here. She'll be up for the Q&A, Ms. Amanda Sandridge. Definitely reach out if you have questions. Navigate is the place to find and make an appointment with her. In terms of accreditation, so we are a relatively new program. Our first cohort graduated in 2022, but we are ABET accredited. And then finally, if you are still interested in biomedical engineering but are leaning towards another degree, we do offer an option for a biomedical minor. So the biomedical engineering minor includes BMES 2104, which is Intro to BME, and then BMES 4064, which is Intro to Medical Physiology. The remaining 12 credits are elective credits that are a biomedical-focused course that offers a lot of flexibility within the current major requirements. All right, plowing through. Student organizations and chapters. So there's a lot of different options for you to get involved, even as first years, to be able to understand what biomedical engineering is and all of its applications. So Bioactivity is a student organization that identifies some sort of need that they would like to address. So the picture up here is actually a bariatric lift for ambulances. That was a couple of years ago. And they're working right now on a lot of wearable technology and interactive technology. eNABLE is part of a national chapter, so this is something that is done nationally, and we've applied to have a chapter here. What they do is they do 3D printing of prosthetics for individuals in need. So this is actually a picture of a child who lives in Salem who they've been designing for several years to be able to give him many different kind of prosthetics for him to do all the different things that he likes to do sports-wise. We also have Undergraduate Biomedical Engineering Society. This is something to help with professional growth and professional development, lots of resume shops and other activities to kind of explore what you might want to do once you graduate. Engineering World Health is an organization that's focused on global health and global health equity. Biomedical Engineering Society is one, again, it's a chapter from a national organization that partners with the Undergraduate Biomedical Engineering Society for a lot of different professional development opportunities. All right, so I will say probably the biggest question I get about BME is, what do I do with this degree? Well, nationally in biomedical engineering, we would say about a third go on to industry, a third go on to a graduate degree, which includes a clinical degree, or a third kind of go on to government or research labs. So pretty much we are on a similar trend to other biomedical engineering biomedical engineering programs. We have about 30% of our students that go directly to industry, and I'll show you some of the companies that they do go to. We also typically have about an 8% going on to medical school or some sort of clinical degree. So that includes pre-PA, pre-PT, pre-med, and all those. I will say if you are thinking about pre-med or any of those clinical degrees right now, go ahead and talk to your advisors about them. There is also pre-health advising here because it's doable with a lot of degrees. Just make sure that you start planning now. So these are some of the different companies that our students have gone to. You see a lot of medical device companies. We also see a lot of car companies for safety development and things like that, as well as the FDA, the Patent Office, and also NIH. We also host a biomedical engineering career fair partnered with Biological Sciences Engineering. That'll be on October 20th. You are able to sign up through Handshake. These are some of the companies that have come in the past, and definitely worth looking into if you are interested in BME. All right. So if you ever have any questions, please feel free to reach out to me. My email is sarina@vt.edu or to our academic advisor.
Thanks. So I'm Dr. Chuba. I'm an associate professor in biological systems engineering. I'm also our assistant department head and undergraduate program director, and I'll talk to you about biological systems engineering. So a lot of you are probably wondering, what is biological systems engineering? And that's because a lot of our department and a lot of departments like us were used to be called agricultural engineering. And then in the early 90s, that changed into kind of broadening that scope from agricultural engineering specifically toward thinking more about water, food, and energy that surrounds kind of the agricultural production process as a whole. And the other thing that happens is that we only exist at land-grant institutions. So Virginia Tech is the land-grant institution of Virginia. We're the only biological systems engineering department in Virginia. You won't find us at University of Virginia. Similarly, North Carolina State University is the one from North Carolina, and Penn State is the one in Pennsylvania, for example. So that's also another part that where we might not be familiar to a lot of you. But really our goal is on creating engineering solutions so where we can develop a more sustainable world focusing on this kind of food, energy, water nexus for human society, as well as what's needed for sustaining a healthy environment. And so really, in terms of biological systems, what we're talking about is at small scales, yes, we're talking about biology, but at larger scales, we're also talking about landscape scales, earth scales. We're really talking about ecology. So if biology scares you and you're interested in, not interested so much in biology, but interested in ecology, there's still that part of that as part of our department as a whole. Our program covers areas from biotechnology to biopharmaceuticals to food production, environmental restoration, and also sustainable development. And so I mentioned biology spans multiple spatial scales, going all the way down from looking at DNA and molecules into microbes and bacteria, all the way up into thinking about landscapes and Earth's surface processes as a whole. So a lot of that fits into these 5 different pathways, one way or another. The top 3 are more of our kind of smaller scale processes in general, and the bottom 2 are larger scale processes. I'll talk more about our specific degrees at the end, but we span thinking about biotechnology. A lot of our students go into pre-med, pre-vet, dental as part of health professions. Food engineering is also a large part, and then thinking about ecosystems and environmental health is also a large part of what we do as a program. So I'll talk more detail on each of these, kind of give you an example of what these actually mean in terms of practice. What do we do in the classroom? What do you do in undergraduate lab research? What would you do in an internship? And ultimately what you would do in a full-time job coming out of our program with a BS degree. So first off, I think one of the things we think about a lot as a department is sustainability. And really the main thing to think about for you all is, where we'll be as a planet in, toward the end of your careers. So right now, we're at 8.2 billion people on this planet. In 50 years, 55 years, we'll kind of peak out at 10.3 billion people on this planet. So that's still another 2 billion people needing resources, needing food, needing energy, needing water. How are we going to manage that sustainably? A lot of what we do across the board are trying to answer that question. Because we not only need to meet those growing demands of society, but we also need to sustain that environment that's going to provide us that clean water, provide us that, that part of what we need for moving forward for sustainability. And so a lot of these grand challenges also stem from the National Academy of Engineers. And so they laid out 12 different areas of grand challenges for engineering. And in our department, we address 8 of these. And specifically, a lot of them I think are maybe more straightforward looking at them, but the last one is also engineering tools of scientific discovery. So in that one, in our biotech pathway specifically, these are the Nobel Prizes in chemistry from the last 7 years. 5 of these are biotechnology related. And these are topics that are being used every day in our BSc labs and in industry that our graduates are using. So if you want to engineer the solutions moving forward, we do this a lot in our biotechnology area. A lot of that happens in our facility, the hobby building on campus, on the south side of campus. These are our biotechnology labs. And in some of those labs, starting out kind of small-scale processes, we look at DNA, we look at bacteria. This is a slide showing how you can use that CRISPR technology to cut DNA into different segments, and you can look at different lengths of those protein or DNA base pairs. And so this is something we do right away in our introductory class that sophomores in the fall semester get into right away, and they also return to that later on during their senior year in some advanced classes. You can also think about injecting different proteins into different cells. This was, I think, if you go back a little farther in terms of Nobel Prizes in chemistry, this was injecting fluorescent proteins into different cells. That way, those cells will fluoresce under ultraviolet light if there's certain chemicals present. And so that's one where we can inject those into cells to look at are certain chemical products being created, or this could be a biosensor of looking at what's happening in the environment. If this chemical is present, these things will glow and fluoresce. And so that's something we think about a lot. As well as this is algae. And so algae and other bacteria, you can use those and feed those algae different products. One common one is thinking about yeast. You feed it sugar, it produces alcohol. There are lots of other chemicals where you can feed it some low-value compound and it'll produce something else through its own biological reaction. These are algae that have been found from some random fountain somewhere, and it's pretty resilient to being fed different substances and producing different substances that are of higher value coming out of those. Another topic thinking about is using biotechnology for essentially soaps. We think about detergents, and really they're not soaps anymore. They used to be soap, but now those are really like things you put in your dishwasher and washing machine are these different chemical proteins, these different enzymes that actually eat and kind of consume and react with the products, not just trying to lift it and wash it away. These are all thinking about biotechnology, within chemical products of everyday industry. We also think about engineering living materials. So if you think about a seed growing a tree, all the information for growing that large tree is encoded in that seed. So how can we think about what is kind of the bio-machinery that's being used by that seed to produce a tree? How do we then take that, thinking about what could be within a single cell, and essentially grow our own wood rather than harvesting it? Thinking about how do you make these living materials. This all kind of stems from this biotechnology, synthetic biology field, which is valued at about $1.5 trillion now. In 15 years, it's predicted to double. So there's lots of opportunities there. I'll talk a little bit more about the food a little bit later in my talk. But one thing is healthcare. And so one example using biotechnology for healthcare is kind of that how we use insulin for treating diabetes. So I don't know, this is 45 years ago, the only way to get insulin to treat diabetes was to harvest organs from animals. And it required 8,000 pounds of glands from 23,500 animals just to produce enough insulin to treat 750 people for only 1 year. And so that's not a lot of medicine, but through biotechnology, some researchers developed a procedure for putting in a gene for human insulin inside a bacterium, using the machinery within that bacterial cell to feed it other products, and it would use that and produce more insulin. And this is how, if anyone's using diabetes medicine today, how they're getting that. It's due to this biotechnology breakthrough that has caused a difference and made a huge difference in people's lives. We also can apply this to thinking about engineering technologies for wound dressing and enhanced healing. We can also think about biotechnology in the context of living sensors. So one thing could be, if COVID-19 is floating around in the air, that virus, there can be other bacteria that react with it and send off a signal alerting you that there's a presence of this virus, and then have other bacteria that cleans the sensor, using this as a way to monitor the air, and also you can do this in the water in different ways. So that takes us to a lot of the small-scale things we've been thinking about in terms of biology and organisms, but kind of stepping back to our grand challenge at larger scales, we also need to think about it from large-scale top-down. And so coming back to what we've done so far as a society in terms of feeding the planet, one thing we've done is intensification of agriculture. So this is a map of fluorescence, which is an indicator of photosynthesis on the planet. And what you'll notice is that there's higher photosynthetic activity in the agricultural Midwest of Illinois, Iowa, into Minnesota than even on this lower spot in the Yucatan Peninsula where there's jungles. So we have so greatly amplified the photosynthetic process by injecting all these fertilizers and pesticides to produce all this food, really just corn and soybeans, at the expense of kind of water quality moving downstream. These areas in green would be all the areas that have agriculture. Through a cascade of biological processes, it leads to dead zones in most of our river deltas, here in the Mississippi River Delta. Even in other channels we have this degraded water quality where you don't have such good water for drinking, and it kind of reduces the amount of habitat for aquatic species. And so even some of these, I'm showing this algal bloom here, but some of the algal blooms you might have heard of in streams and in lakes, those are even creating toxic substances that are harmful for your dog to drink it, and your dogs can die through that. A lot of it comes back to the same thing of feeding into these nutrients. So a lot of what we're thinking about, even at these large scales, is coming back to sustainability. How do we both meet those needs of society and of these ecosystems, making sure they're clean and healthy? Some of the ways that we do that, here we're thinking about floodplains. There's an arrow showing the river channel. So at different times you get water flowing across this floodplain, and what are the processes that are trapping and bringing in some of the sediment, bringing in those nutrients. We think about physical processes for how do we apply physics and fluid mechanics to moving water, and then how do we think about chemistry and biology in some of the physical transformation and some of the transformations that are going to happen to those contaminants within there. So thinking about how these multiple pathways can start acting as a way to treat some of that those high nutrients in the river channel, moving downstream. To avoid those algal blooms. The other thing we think about is restoration. So this is one thing we definitely do not want to do. We don't want to send out engineers and recommend that to prevent stream bank erosion along this river, you just dump a bunch of construction debris along the bank, and that stops it from going. We instead, focusing on ecological engineering, we want to engineer an ecosystem, right? So here along this stream, it's thinking about how do you get the right mix of plants and processes where that water is going to flood that floodplain, reduce those nutrients, make a better ecosystem, more habitat for these different species. And so we do this through doing different measurements out in streams all the time, measure the size of the rocks, measure the geometry of the channels, getting out there. Those are the things that we can use together with our math and physics to estimate what's going to happen in terms of habitat. We can also measure water quality and water quantity that's coming through. This is a sophomore in my research group that was out with me last May. So she was just at the end of the sophomore year doing some field work, collecting sediment to look at suspended sediment in this river system. We cover a lot of these processes of getting out into the environment, doing these measurements for supporting our engineering methods. One of those classes is Field Methods in Hydrology. This is a class that taught at our senior level. We go out to the New River, we go out to other rivers nearby, and this could be you in 3 years, within our department. Another thing we talk about is floating treatment wetlands. So here there's the context coming back down to food now, where there's these catfish ponds where you grow catfish, but then they produce a lot of nutrients, and that can lead to harmful algal blooms and then kind of kill the catfish at some point. So one way is to pair it with these plants that are floating on top, that those plants can take up those nutrients, and so then you still have the plants and the catfish can do better. So then again, this is another one where a lot of these students in this picture are undergrads in our research groups. We also think about aquaponics. How do you develop a closed system for growing fish, using that waste from that fish water to support, I think this is a lettuce that's being grown, using those nutrients to support those lettuce and then recycling that water back into the fish. So creating this closed system where you're using more of the nutrients all internally and you're not wasting any of these products. Another aspect into fish is thinking about sustainable food, right? We can't just have more and more beef and more animals. We're kind of taxing the land that we already have. One way is thinking about alternative foods. This is one, showing both engineered chicken and also meats. Those meats, one of the key ingredient, you can get the texture right, but getting the color of that red blood-looking substance, that actually comes from the soybean plant. There's a chemical in there that gives it this coloring that people expect when they bite into a red hamburger. So that's another thing we looked at. And on top of all this, of all these things we're trying to do and these challenges in this year, climate is also changing. So what that means is that we're going from a world where conditions are as usual, even from just thinking about water flow on our landscape, we're now getting more rainfall in shorter amounts in small periods, and at the same time we're getting longer and more devastating droughts. So it's not about, okay, we're going to get more water or less more water. It's about the water that you are going to get, you're going to distribute it differently throughout the year. So where we're going to give you're going to get more rain sometimes and less rain other times. And we need to work within that environment. So one of the other things we look at in terms of urban stormwater, rather than just letting water run off into gutters and curbs and into streams, is determining methods where creating a little ecosystem in those urban environments that's going to help filter out some of that water, withhold it, slow it down, remove some of those pollutants from it, provide some habitat and other benefits on urban cooling. And there's plastics that are everywhere, right? So there'll be more plastic in the ocean than fish by 2050. I think the trajectory we're on, I wouldn't be surprised if we far exceed that. So some of the things we think about, coming back down to the biotechnology world, is how do we develop new functional materials that provide the same benefits as plastic but biodegrade more readily, made from products that are easier accessible on the environment. And so coming all back to it, we've kind of given a broad tour of a lot of these different areas in biotechnology, what can tell you what direction we go in terms of health professions, food engineering, environmental health, and ecological engineering. Our program has currently 2 degrees, one being ecological engineering, that's kind of highly specialized in kind of the bottom 2 aspects of this plot. And then we have a broader degree which covers all 5 of these, and you can kind of choose your own adventure in terms of what classes and experiences you want to take in that program. Our expectation is that within the next year we'll have some sort of biotechnology major as well that you can specialize in, and that should be coming along soon. And so one thing you might ask is where do we go from here in terms of jobs? These are all the places our a lot of our students more recently have ended up after graduating with a bachelor's degree. More than 90% of our BSc graduates have a job within 6 months. And there's the 68,500 is our median salary that's just with a BS, that's not with a graduate degree. And so that's a little bit, that'll be higher. It could be upwards of 80 or 90 going into the pharmaceutical and biotechnology companies. It's going to be lower if you go into a nonprofit organization. And it's probably right if you're going into some of these environmental consulting firms thinking about ecosystems. And so I'll end it here just to mention that of our peer degree programs across the nation, here at Virginia Tech, we are the 8th ranked program in the nation. I think that number is going to increase over the next year or two. But there's our website, bsc.vt.edu. That QR code will also take you to our website. My contact information is there, as well as our undergraduate advisor, Ms. Baker. And we'll be around at the end of all this at our booth just outside to answer more questions you might have. Thanks.
Good evening, everyone. My name is Michelle McKellar. I am the undergrad academic advisor for Material Science and Engineering. Just going to dive right in. How many of you, a couple of you indicated you're interested in material science. So for everyone else who is unfamiliar with us, we are the study of how things behave, why do they do naturally. Excuse me, I dropped my glasses. The study of things and how they behave, what do they do naturally, and then we engineer it to do what we want it to do. There are 4 basic materials that we work in: ceramics, polymers, electronics, and metallurgy. Before I get too far into this, I want to ask you guys, what can you make without a material? Nothing. I'm going to take a couple minutes and talk about the tennis racket, and we're going to talk about the evolution in that sport and how materials has played an important key factor in it. Tennis was first invented in the 14th century, and they used their palms as a racket. Okay, so the ball's going back and forth and you're using your palms. It wasn't until the 14th century that they invented some kind of wooden paddle with strings on it. Anyone know what those strings were made out of? Any guesses? Pig intestines. Close. We used sheep intestines. Okay? It wasn't until 1870s that they decided to use string instead of sheep intestines. Okay? So how many centuries of sheep did we use to make tennis rackets? All right? So this is an improvement in the sport. Additional improvements have been made since, and these are changing the racket. We haven't changed how it's designed, but we have changed the materials that go into it. How many play tennis in here? Anyone? Okay. Do you guys play with a wooden racket or an aluminum? Right? There's a difference in the two in the way that they handle because one is lighter than the other. Right? Next, I want to talk about skateboards. Any skateboarders? A couple of you. Okay. So the important thing on skateboarding is that it's a composite material of different woods and grains and how they are stacked together. Okay? We've gone through many different improvements in that, from those small, thin plastic skateboards to the big wooden ones that we use now. But more important in the skateboard design is the bearings, the ball bearings that they use in the wheels and the wheels themselves. Early skateboards used metal wheels. Right? That's not very good. They don't last as long. They don't slide across the ground as easy. So they eventually developed the polymer wheels that we have today. Any runners in here? Runners, okay. On average, your tennis shoe and your running shoe will last about 1,500 miles. A material scientist challenges to make that last 2,000 miles or 2,500 miles, okay? So how do we extend the life of that? And material scientists are working with Nike, Adidas, and Under Armour and looking at the polymer on the bottom of your tennis shoe and how we can improve that so that that absorbs the shock impact of your run and it doesn't go to your knees, ankles, and hips. Okay? And finally, the football helmet. Right? This is an early rudimentary design of a football helmet. We actually had Sarah talking, where'd she go? She's right hiding from me. Talk about the helmet and the helmet lab. Material science is very key to that because you want to use the right plastics and polymers, and the foaming on the inside of that helmet has to be precise so that that absorbs the impact and it doesn't go into the skull and the brain. Okay. So material science and engineering is the center of what I call the center of all engineering. You can't make something without a material. Whatever industry you're going to go into, there is going to be a material scientist saying, this is how you make it. I'm going to pause right now and just ask how many of you have ever made a cake from scratch? Okay, a good number, good number. For those who haven't, I challenge you, when you go home for Thanksgiving, make the cake from scratch, okay? Take that off of mom's hands. Say, I got this for you. Make it from scratch. Now, the ingredients and the directions are going to say warm butter and sugar. You mix those two first, add egg, add oil. In a separate bowl, you're going to add your dry ingredients and mix those up. Eventually blend and bake, and you're going to have a fabulous cake, okay? She's going to be so happy that you did this that at Christmas, she's going to ask you to do it again, okay? Christmas, I want you to mix up the recipe, okay? Add the egg to the flour, then the salt, then cold butter, and see if you get the same cake. Anyone have any guesses? No? All right, so that means all of you are going to go home and do this. Fabulous. All right, so here we can see that whatever industry you're going into, there's a material scientist there working, all right? Again, what is material science and engineering? The study of how, and then we engineer it to do what we want it to do, okay? Within our program, we study the 4 basic materials that I mentioned. We also have 12 credits of a technical elective. These can be engineering specific, engineering related. These are all designed to enhance your problem solving skills, okay? We have a communications and professional development program built into our program. So every time you're writing a paper, our communications team is there with you, helping you write that paper, and so you always get an A on your paper. This includes lab reports, okay? Speaking of labs, we have planned correctly, our students are in the lab every semester. From the moment you enter MSc until you graduate, you're in the lab doing the work. We intentionally keep our labs small at 12 or few students so that you're the ones doing the hands-on work. You're the ones pouring the hot glass, the hot metal. You're the ones playing with the stuff. Like all the other engineering disciplines, we have a capstone senior project where we have groups of no more than 4 students working on a project from beginning to end. Our past research projects have been things such as tissue regrowth, bone regrowth, wound healing. We've had several medical ones. We've had students do surfboards, all right, that final wax coating that's on a surfboard that helps it stay smooth and water resistant. We've had those. We've had students do diabetes studies on hair follicle. Can you detect future diabetes with a hair follicle? Right? You name it, our students have researched it. We've had a senior design team work in the biomedical area where they were trying to create a catheter that could be implanted and seen on ultrasound. Right? That's huge for the medical industry and huge for the pediatrics. Because right now these catheters that are implanted, that you can't see them on ultrasound, you can only see them on the x-ray. So that's not good for an infant or small children because we don't want to expose them to that x-ray. So if we could invent something that the material is impregnated so it can be seen on sonogram, that would be helpful. So these are the various types of things. Any students in here working on an honors degree? We have an honors program and we can turn some of your technical electives into honors-related courses. All right, I don't think anyone has mentioned yet tonight the accelerated program, but we do have that. I think most of the engineering disciplines do, so that your 4th year in your undergrad is your 1st year in your grad program. So you can get an accelerated master's degree in 5 years instead of 6. Okay? This tetrahedron here is basically another view of what MSc is. We're looking at the structure, the characterization, the properties, the performance, all of that and goes into the characterization so we can get the best outcome for all of our things. MSc, we are one of the smaller departments. That's to our advantage, I think. I am the single advisor for the department. I get to meet each and every one of the students. We have 26 full-time faculty working, and right now there's about 125 undergrads. So you will get my undivided attention. At most, we've had 225, I think it was. Currently have about 70 grad students. Is that? No, that's the mouse, okay. Like I said earlier, we have the labs, and all of our students participate in each of the labs every semester all the way through. So extracurricular activities, there are a ton of them. Our students right now are preparing for an MS&T conference, which is going to take place at the end of October, early October. This conference is a design competition conference where students will go participate in conference-related events, but they will also participate in challenges against other students from other colleges. We hold a record for several of these challenges. You all are familiar with like a mug drop competition, correct? Yes? Okay, I see a few thumbs ups. So it's basically we have to design a mug and drop it. The one that can drop from the highest without breaking or destroying its structure wins. We have won that record a couple times. There's also a disc throwing contest where we build a ceramic disc and you have to throw it into a the Frisbee golf net. All right? We also hold the distance for that record. There's other competitions which we're not participating in at MS&T this year, such as the geodesic dome, where we build a dome and weight is placed on it. The lightest weight dome that holds the most weight wins. We have won that contest 4 years. They stopped offering it to us. So we can't win it a 5th year. The MEPS organization is Materials Engineering Professional Society. Every student in MSE is a member of MEPS. Then there's other various ones. ASM, JUMR is an undergraduate journal for students who do research. So as an undergraduate, you can have your research published. American Ceramic Society, there's now the Nuclear Society, and I don't need to read those all to you because you're here. So after graduation, what will you be doing? Well, there's several different options you can take. You can go to grad school, you can go to work. Right now, I did this research last week. Bureau of Labor Statistics indicate median salary is 108. Now remember, that's median salary, so you're not going to get that right out of the gate. But the job rate for material science is growing faster than the other industries. And these are a few of the places that our students have either worked or co-opted. I like to say that MSc students are everywhere from Yankee Candle to NASA and anything in between. So wherever they're building or making something, there's material scientists there. All right, and just to show you, material science alum at work, one of my students who graduated in 2015 helped design this climbing rope. Okay? So your material, your product will be sold, and that's awesome. So after graduation, as I mentioned, you go to grad school or go on to employment. We have the 5-year program. We also have some of our alum going to these various colleges for their master's or their PhD. And I'm gonna, material science and engineering, we are Hokie Material. Thank you.
All right, everybody. Good evening. I need everyone to stand up. Everyone stand up. You've been sitting down for a little while. What I need you to do is turn to your left, turn to your right, and high five the nearest Hokie to you. Congratulations. You have successfully made it here. We are thrilled to have you. Now you can sit down. But we shouldn't forget the fact that you've done quite a bit of work to get here, and we're so thrilled to have you. And no matter what department you choose, we know you're going to be successful and have a great time here at Virginia Tech. So welcome. My name is Chris Williams. I'm a professor in the Department of Mechanical Engineering. This is my 17th year here at Virginia Tech, and it is wonderful. So I'm here to talk to you about what a mechanical engineer does. And my number one pet peeve about mechanical engineering is when I ask people, what does a mechanical engineer do? The first icon they want to give me is a bunch of gears. So I had roommates of material science, awesome roommate, an aerospace engineer, another awesome roommate, and we would spend time in undergrad debating about, who was the real engineer or, what who was doing the coolest stuff, and they'd be like, oh, you just go play with your gears, and it's like, no, that we do so much more of that. Like, oh, hey, can you fix my car for me? Many of us can. Or, go play with your little toy robots. Mechanical engineering is so much more than machines. Now, we do really awesome jobs with machines, not gonna lie, very proud of it, but we're way more than gears. And so mechanical engineering is the broadest of the disciplines, we would say, and it includes everything from systems to, of course, design and manufacturing and robotics, but also nuclear engineering and science, and also energies and fluids. Essentially, when you look at all the topics that we work on and that you can study in our department, you'll see a wide variety of things. Effectively, we are involved in any generation or distribution or use of energy, any processing of materials, any making, any controls and automation, essentially that's a very adaptable and versatile degree. If it's something that is physical, that has been made or moving or transferring or using energy, you better believe a mechanical engineer was involved in that process. Fundamentally, what I believe we do, and I think a lot of us engineers do, is no matter what you study or focus in, fundamentally we're in the business of making things real. We take the design process, we take all that we've learned in these engineering science classes so that we can analyze and identify the best solution, we put all the pieces together, we build and make it, and then we test it. That's what we do at mechanical engineering. And we really, basically any artificial thing that you're holding, yes, it was made in the material science department, but, so no, that's very true. But really, if it's designed and manufactured, which is basically everything in here, some mechanical engineer was involved. Just this past 2 weeks, I've had a chance to travel to different very large companies at Virginia, across our Commonwealth of Virginia. One was the Newport News shipyard, and every employee I came across was a mechanical engineer as they're working on literally building our nation's nuclear submarines and aircraft carriers. And then on the way back, I stopped in Lynchburg at BWXT, where they make all the nuclear reactors that go in those submarines and aircraft carriers. And the majority of their employees there, they had some really awesome material scientists and industrial engineers and chemical engineers, but the large majority of them were mechanical engineers, because that's what's needed to be versatile and adaptable to these very, very complex systems. Everything from designing the components themselves and making them, but also figuring out how to actually design a nuclear reactor. So let's just take a quick peek at some of the things you'll see. One of the things I love about our department is that we end our senior year with a full academic year capstone design experience, where we partner you with an industry partner, a company, and they give you a real problem to solve, and you work with your team and your faculty advisor to go off and solve a real industry problem or need. And these can be everything from a bobsled launch pad for differently abled folks who are training for the Olympics, creating really large rotorcraft, looking at ways in which humans and robots can work together, and of course, like any good mechanical engineering department, building lots of moving vehicles. We've got so many different, this is a snake, sort of a robot-like thing. We've got lots of good opportunity. You'll see that every project ends with the design, building, and controls of a physical object. So if that's something that appeals to you, this is a great department for you to sort of learn the skills that you get along the way to then deploy. We've got our electric vehicle teams, our Baja teams, formula teams that are more very interdisciplinary. Yeah, it's a great experience. And you'll see that we end that big day in the stadium where we get to show off all of our things, including our snake robots, to our industry partners and alums who come back and judge and pick out the best design. So a really nice way to end your experience. Again, even exoskeletons, so helping robots help humans, more manufacturing processes, and of course Baja, you gotta have Baja in there. And formula, you gotta have formula in there, of course. I think that's a nuclear fuel cell reactor, handling device. More moving stuff, very cool. So really happy seniors. So if we don't do gears, what do we do? So what is the future of this? So when I was in school a while ago, people are like, oh, the internal combustion engine is going away. You've got to find a new degree. And thankfully, they were very wrong about that. They're like, oh, electrification, that's the future. And it absolutely is the future. But you need mechanical engineers who know how to design and create the systems that those things support. We are the future and the home to a lot of autonomous vehicle software, swarming, collision avoidance, robotic human interaction. And we are all about mobility, so creating the next generation of aircraft. We're, of course, the aerospace engineers are the ones designing some of the aircraft, but all the power distribution systems and all the controls, that can be done by mechanical engineers in collaboration. Helping people with mobility with those exoskeletons and robotic assistance is also key. And we're also the future of manufacturing in terms of, again, robotics, controls, and automation. And also the future of manufacturing. We do a lot of additive manufacturing or 3D printing in our groups, in our labs here at Virginia Tech. And in the future of robotic, cadet-assisted push-ups as the Hokies scored yet another touchdown. That's been done by mechanical engineers. Another touchdown is what I said. You're supposed to cheer at that part. Okay. So yeah, there you go. All right, so some alum, okay, that was too much cheering. It was too much. All right, so some alums, what do our students do? So I'll talk a little bit about some of the alums that came out of some of my classes. So for example, we've got Grady in the top there, and we've got Genevieve, and they're at SpaceX with Josh. So Genevieve's done all the design work on this, the new heavy rocket and done a lot of those hydraulic controls of the steering grids. Grady in the top left actually was the first person to actually print some of their Falcon 9 rocket engines. He came out of our lab and then went and started doing all the design and manufacturing of those new engines. Michael Barclift went off to GE, and he was actually responsible for the world's largest 3D printed sand mold to then do metal casting, also taught at the materials science department. And we've got Stephanie here went out, and she actually also went to GE to do lots of really cool engineering things, but she also had the chance to actually design and 3D print a dress for the Met Gala a few years ago. And Ed actually went off to Relativity Space, where they were working on robotic 3D printing of entire rockets, and actually last summer was their inaugural launch, all done and enabled by Hokie mechanical engineers. So again, it's a very broad department, a very broad discipline, and our key focus is in these areas of advanced manufacturing and design, bioengineering, so we have people actually doing cellular dynamics and things at the micro and nano level, even nanoscale robotics. We also, of course, have robotics and autonomous systems. We have a whole minor and air focus area in nuclear engineering, and then dynamics, vibrations, and acoustics, the way that things move and translate motion, energy systems, mechanics, and our favorite, thermal and fluid sciences. So what I thought I'd do with our remaining time is just highlight some examples of some of the cool things that our faculty are doing in collaboration with our undergraduate students. And again, to sort of give you an idea about how our faculty think about the future of the discipline and really help understand that the cool things they're doing are really enabled by the fundamentals that they and their students have learned in the field of mechanical engineering. So for example, Dr. Ray Makers is actually working on the future of 3D printing. He's created a 3D printer that actually has ultrasonic transducers around the build plate that actually allow you to align nanofibers according to design. And that's a technology enabled through, again, mechatronics and automation, but also knowledge of fluid dynamics and acoustics. So putting all these different pieces of the discipline together to invent the future of manufacturing. And he can do that layer by layer, changing the field and changing the orientation of those fibers as he goes, which allows them to actually, in this case, actually align silver nanofibers to get really highly conductive, selectively conductive regions, which allow him to think about, completely single part actuators, being able to put electrical components together just by the push of a button. And again, that comes down to designing structure and understanding how the mechanics of that come together. Let's check another example. This one comes from my lab, which is sort of the integration of some robotics and additive manufacturing. So we're thinking about the future of how you might 3D print things. Instead of it being in a box, shouldn't it just be one of many tools? So this is actually a senior design team formed by about 9 students who worked over the course of an academic year. And I said to them, I want you to make a 3D printer that can print an entire drone, and I want the drone to fly off the build plate when it's done. And I don't want any human involvement. That seemed like too easy. No, it seemed impossible. But they actually did it because they're Virginia Tech Hokies. So the first thing that you saw was hit printing. The robot's wrist switches over and actually picks and places the central module. This is the cool part. It actually grabs the rotors, slides them into connectors, and then pulls out this pre-stored wire and then sits into place. It does that for all 4 rotor blades. And by the way, Kieran is now working at an engineering firm down in Florida. And you saw Heather in the back there. She works at Savannah River National Lab doing some cool robotics work. So now they go back to printing and actually embed all the electronics and make sure they're all stuck in there. Eric is now a graduate student doing some cool robotics work, and he actually has a controller, but what he's controlling is the drone. He's gonna be the pilot. So that robot's then gonna add a battery, and then because you gotta have one, he's gonna throw in the GoPro. Jimmy in the back there in the white shirt is actually a business student and helped a lot with the marketing and cool stuff. So you're gonna let that part cool down, and then you're gonna eject it automatically. No one's touched this, and then it just flies away. And this drone's mission actually is to land and then film the next drone being made. This is an H-frame drone. It's sort of shaped like the letter H. But what this one is actually going to print next is the X-frame drone. It's a whole different drone design, same concept, and then the drone's going to fly out of the garage and onto its next target, which is Eastern Divide down the street, which when you're juniors, you'll understand what Eastern Divide is, and you'll really enjoy it. Anyhow. So yeah, it keeps going. Pretty cool stuff. So again, undergraduate, senior level mechanical engineers coming together to solve problems around materials, design optimization, CAD, robotics and mechatronics and controls to enable something that literally no one has ever done before. That's what we do here at Virginia Tech, is invent the future. Speaking of inventing the future, Michael Bartlett, a good friend of mine, also has been working on drones. He does some really amazing smart materials. So you see those sort of silver things in there? That's actually a special metal alloy that actually is easily melted and gets soft. So actually this car drives off on a heated plate, and actually it heats up that silver ink, which all of a sudden gets really soft and transforms. I don't know if you all know Transformers. You know Transformers, come on. Everyone. And then you let it cool back, and now it's locked into place, and now you have this transforming car drone vehicle thing. Never been done before, but done here at Virginia Tech with mechanical engineers in inventing new materials, inventing new manufacturing, inventing new controls that way. But we do more than just hard things. We also do soft things. So Noel Naughton actually has a real octopus in his lab, so check that out. I'm afraid, I hope it doesn't get out. But he's all about this idea that, to make the next generation of robotics, they have to be soft to be able to adapt to our complex environments and work around humans. So why not look at the way nature does that, which is an octopus, which apparently, according to these notes right here, an octopus has a brain in every single one of its arms, which he put it there, so I assume it's true. But they're using their experimental techniques, their modeling techniques to really understand the biomechanics of these arms. And basically the idea is they're going to try to take these lessons and simulate them and then develop controls and artificial, man-made structures to mimic the capability to enable the next generation of robotics. Dr. Soha has been here. He came in the same year I did. And if you hate flying and you hate snakes, I've got bad news for you. There's this thing called a flying snake. That was a good joke, actually. I'm not gonna lie. Flying snake. So take an eye in the top left there. So these are not in North America, except in Dr. Sosa's lab. But his lab also looks at the dynamics of biological mechanisms, and he's studying all things that fly. So he's been working on the mechanics and dynamics of flying snakes for quite a while, and now moving on to flying fish, flying squirrels, flying lizards. If it's flying, he wants to understand that, and he does it through this combination of biology, X-ray imaging, dynamics, and then applying them on to mechanical systems. Another professor who does something similar in that vein is Dr. Mueller. He's actually a real expert in bats, sonar, right? So, bats we know have such great echolocation capabilities. It turns out the way they do that is actually by dynamically changing their ears. So he's actually gone to China several times and studied and captured bats and brought them back. And his students, as part of their senior design project, actually 3D printed a soft ear and made these soft actuators to actually make the ear flex just like the real thing, again, in the hopes of being able to replicate that for mechanical systems. Pretty cool. That's all done by seniors. Dr. Borrico is taking the combination of lots of things in mechanical engineering, from fluids to heat transfer and some other surface tension dynamics, and actually bringing them to a problem to help actually conserve and actually save water.
So the fog harp was
And I'm going to.
invention specifically inspired by certain types of coastal.
He's talking. That's Dr. Kennedy. He's great. He's with industrial engineering. Here, can I?
Water droplets.
I
from
am
the
hitting the
fog,
button.
which end up rolling off their needles and onto the
I
forest
just wasn't
floor.
patient.
First, we just suspend a fog harp structure in a very foggy area. As the fog comes in, microscopic water droplets get caught on the wires as the wind passes through. These droplets eventually grow large enough to zip down the wires into a bottom draining collector. This collected water can be used for drinking water or also for irrigation and agriculture.
I think it's a really big opportunity to look at nature. Nature is a huge repository of design and engineering insight. So it seems almost silly not to examine it and see what's there and see what can be gleaned from it for the benefit of society.
So personally, my favorite part about being a mechanical engineer is it provides me the breadth to be able to partner with other people to solve really complex problems. So I do a lot of work with good friends in material science, chemical engineering, industrial engineering, and you saw there collaboration between mechanical engineering and industrial design to create new things. Let me share just two more examples. This time, yeah, buddy. In this case, Dr. Asbeck's lab, who's looking at the next generation of robotics and then interfacing with humans. And this is his large senior design team, who was actually tasked a number of years ago to create a new exoskeleton that actually a human could wear and it could augment their behavior. The very first senior design team that Dr. Asbeck had on this was actually sponsored by Lowe's. The resulting passive exoskeleton is now a startup company here in town. So a lot of the students actually stayed on and started their own company. Meanwhile, this Iron Man suit is pretty wild as they're being able to use this to pack heavy things. So when we look at the future of manufacturing and helping students, manufacturing folks or even rescue folks be able to lift and carry heavy things with just their pinkies, it's pretty awesome. Again, it's mechanics, it's controls, it's dynamics, all done by students. As you can tell what year that was. All right, we'll close out with one of our newest faculty, just joined, is Simon. I love the overcooked analogy, pretty funny, but basically this idea of how could humans and robots work together to solve complex tasks together, in this case, collaborative cooking. So while the human does some cutting, the robot's off doing some other components of that. Again, it's all about AI, data, robotics, and controls. So we're excited that he's joined us. And one last piece is Dr. Comandera's lab. You take all those robotics and you put them in space. He actually came to us from NASA Langley, and he's doing a lot of work in how robots can be shipped to extraterrestrial places to actually identify objects on demand and grasp them and take them home, or actually having robots work together to assemble large objects. And we've even had work together on large-scale 3D printing of Martian structures. So lots of fun to be had in mechanical engineering. We're so glad you're here with us. And if you have any questions, please feel free to ask all the awesome ambassadors we have coming up on stage next. But welcome to Virginia Tech. We're so glad you're here. Thanks so much.
Awesome. Thank you all so much for your patience tonight and for being here. Really appreciate it. The first night of Explore Engineering is going really well, so good attendance tonight. So we do have some questions that we're going to ask our panelists here, and then we're going to ask the one question, and everyone will have an opportunity to ask that question or respond to that question, and then that will conclude our evening, and I'll tell you kind of when we're there. So the first question we have, we'll start with you in biomedical engineering, is why should a student consider your degree? Okay. And you can leave it where it's at. We just need to unmute it, and you'll just push the button. Yeah, and the rest of you the same thing.
Okay. So I think that our degree is really cool because we do a wide variety of things across the medical field. So you can do anything from cancer research all the way to large-scale medical devices or stuff that's going on in the OR room. So that's really unique. And also we get to pick a lot of our coursework. So all of our technical electives, we get to pick 7 different classes of just what you're interested in. So that is really special that we get to take those classes truly in just what you're interested in and not what you're required to take.
Okay, we can talk a little bit about BSc. I'll go first. One thing that was mentioned in the PowerPoint is with the BSc degree, you can choose between those 5 different options. If you're in the BSc major, the ecological one is a little more straightforward. So if you're kind of unsure, if you want to do water stuff or biotechnology, you have a few years to figure that out until you really have to hone in on what specific classes you're taking. We take the same classes at least the first year when you're in the program, and a few people switched and still graduated in 4 years.
Yeah, I would say one of my favorite things is that you can be unique. You can not be like everybody else. You can really make this major and your time here what you want it to be. So our major it can be pretty broad. There is like a common theme, but from the outside, maybe it looks like there's not a lot of like the sameness, I guess. But you can really make the major what you want, make it unique, do some crossover, be multidisciplinary, get involved with other departments, other things that interest you, make it what you want.
I just want to first say that my students couldn't be here tonight because we're hosting Nucor, and they are all taking care of that tonight, so it's me that you get. So why should a student consider MSc? It is very broad, very diverse. You can focus and you can tailor the degree to your interest, and it's an exciting degree to be in right now.
One of the things that I think is pretty nice about mechanical engineering is, I guess, dittoing what a lot of these people are saying. It's very broad. The fundamental kind of physics and engineering that you'll learn in a lot of your classes are kind of applicable to any other engineering discipline. So you have that fundamental fluids knowledge, that fundamental statics knowledge that you can kind of use in going about just what you want to do when you start to look towards, okay, well now I'm interested in this, and you can kind of apply what you've learned as a whole in mechanical engineering, and just kind of having that wide breadth is really advantageous, I think.
Excellent. So our next question we have is, what was the neatest aspect of your undergrad experience that you've taken advantage of so far?
Okay, so my favorite experience was I got to study abroad last fall in Australia. So I got to take some engineering classes over there, and then I also have a psychology minor, so I got to take some of those over there. And so just getting to spend 4 months traveling around Australia, New Zealand, and Fiji was really definitely the highlight so far.
My favorite, or one of the neatest things that I got to do was just get involved in so much professional clubs, research, even the BSc design team. I got to do so much traveling, got so many opportunities, traveling to conferences and competitions. Over the summer, I got to travel to Toronto for a competition. That was really cool. And also, previously, like mentioned in our advisor's presentation, was the fact that BSc at Virginia Tech is a land-grant university. So we have this one major is at one college in each state, or every land-grant university in each state. So when we go to these different conferences, we get to connect with people that are doing the same unique things that we're doing here at the other universities, which is just a unique experience that we all have.
I'm going to answer this in a little bit of a different way. As me, the advisor, and what I get to see with the students is I meet with each and every one of them independently and work with them throughout their 3 or 4 years here. And I get to see them evolve and grow and decide, I want engineering, I want materials, which material do I want? And it's that complete evolution and the growth process for all the students to figure out where they want to be in their future. And my job is to help them get there.
I think the coolest experience for me in ME has definitely been my design team. So I'm the co-president of one of our design teams, which designs, builds, and races electric motorcycles, like crazy, super fast, super bikes that go like 200 miles per hour. And the cool thing is it's completely student-led, student-run. And I joined as a sophomore, you can join as a freshman. And everything you learn is just from seniors who have gone through the classes you've gone through. They can help you like talk about professors, talk about your homework. It's a really great community because you make a lot of friends, and you also get to work on something that you get to like see go to a race. So you get to make something real and put it on a real bike, and then it gets to go do a real competition. So that's definitely been the coolest experience I've had.
Excellent. So the next question we have for you all is, as students are trying to determine the best degree for them, what is one piece of advice that you would give them to help make that decision?
So I would say pick something that you're truly interested in. Take a look at all the classes on the check sheet. Make sure that they look interesting to you and like it's something that you could see yourself doing in the future. That will make your degree a lot more fun, a lot more enjoyable than like dreading going to class every day.
And also talk to some of the students that are in the programs that you're interested in to learn about their experiences, because what you think something may be is probably not even close to what it is. So always talking to some of the juniors and seniors in the programs, very helpful.
Okay, not that I'm recommending this, but I changed my major 3 times. I was in filmmaking, marine bio, chemistry, and then I finally ended in BSc. So just because you think you want to do something right now doesn't necessarily mean that's what you're going to end up doing. So like they were mentioning, do your research, talk to people, look at what jobs are hiring people from the program you're looking at. Look at the job description. Is that something that you could see yourself doing in 4 years? If not, maybe you should look somewhere else. So that's what I would recommend.
I'm just going to echo what they said, and yes, you want to talk to people. Not only do you want to talk to current students, but if it can be arranged, talk to an alumni, someone who's been out in the industry for maybe 2 to 5 years, figure out what they're doing, what they like, to talk to about their education while they were here. There was one other thing, and it slipped my mind.
Yeah, I definitely agree 100%. You're not locked into your choice. It's never too late to switch things up. If you start and decide, hey, I want to do mechanical engineering, and then you get into it and you realize maybe this is a little too broad, I'm kind of more interested in, I guess, maybe specifically aerospace application, then it's not too late to switch. A lot of your classes can potentially have that transfer credit availability, and definitely pick something you're interested in. I agree with looking towards potential jobs that have the kind of tag of like, this is what a mechanical engineering job would be, or this is what a BSME job would be, and see if those jobs are interesting and if the job descriptions is something that you would want to do, because your major can be really interesting and something that you truly enjoy, but the job market might not necessarily reflect exactly what the course load is. So you should do your research into what the jobs that you want to have require in terms of your degree.
What an excellent punt over here, because what is going on this week that you can check out employers? Engineering Expo, right? So definitely go by, check out the employers, visit their tables, see what they have to offer. Even if you're not looking, I highly, highly recommend that you at least just walk around so you can get a feel for the next year when you might really be looking for something. So definitely just go, even if you're just browsing. All right, so the next question we have is, and maybe this doesn't apply to you because maybe you've got the fullest potential out of your whole experience here at Virginia Tech. But what do you wish you had taken advantage of during your undergrad experience that you reflect on now that you wish you had?
Okay, so I would probably say going to office hours, that can really help foster your relationship with professors. And even though you can go out and you can get research opportunities and you can get internships and co-ops and you can do all of that on your own, it can be make or break knowing professors that have those connections already formed. And so if you have a good relationship with them and they're frequently seeing you one-on-one in office hours, that can really help get you some good opportunities that you might not find on your own.
I would say I really don't have regrets, but I definitely did at the beginning. I transferred here, and the first year I just spent like kind of alone, didn't really know how to be a college student or what I was supposed to be doing. But eventually I broke out of that. I started exploring. I did anything and everything I thought was cool. One of the best pieces of advice I was given was opportunities will find you if you seek them. So basically, even if you don't know what you're doing, just do something, and one thing will lead to another, and eventually you'll get somewhere. So yeah, once I started doing that, I got to do everything I wanted to do, everything I didn't know I wanted to do, and now I really don't have any regrets.
The one thing I would recommend for you guys is to find clubs, groups, organizations that you can be a member of. But the important thing is that you have a lot of commitments already with your class time. If you think about this, if you're taking 15 credit hours, the minimum amount of time outside of the classroom you need to be spending is that 15 hours times 3. So that's 45 hours outside of the classroom that you need to be spending on your coursework. And that's just to do well. If you want to do really good, it should be times 4. Okay? So with that in mind, you still want to be active and find these groups and clubs and things. But the important thing is to find groups and clubs that you can take a leadership role in. And right now, as a freshman, you probably can't, but later on, you can. And you want to be able to put that on your resume and say, I had a leadership role in this club, instead of, I was a member of 15 clubs and I did nothing. Right? So around here, engineers are a dime a dozen. You need to stand out and be that little 2 cents that I say. So you want to get involved in maybe 2 or 3 activities or clubs.
I have 2 things on this. One of them is take advantage of the freshman design spaces. The Frith Lab, and I know the Galopecia LLC might also have a design space in the dorm. I don't know if it could, back when I was a freshman it was in Hogue, but that might not be true anymore. Take advantage of that. When I was a freshman, I didn't truly realize I wasn't gonna have access to that when I was living off campus. And then my sophomore and junior year, I kind of was like, I wanna do these hands-on projects, but I don't have drills, a tool set, didn't have a 3D printer at the time. Having free access to drill presses and bandsaws and 3D printers is really, really nice for doing personal projects. And it's something that's a lot harder to get access to when you're not a freshman or if you're not on a design team. And then the second thing I would say is try and strike a really good balance between focusing really hard on trying to improve your academic resume and have strong qualifications for the jobs that you want, but then don't forget that you're trying to have this holistic college experience. And there's a lot of really cool clubs and organizations at Virginia Tech, like Chocolate Milk Drinking Club or Chicken and Waffle Club on Fridays, which is literally just they get together and eat chicken and waffles from the Southern Comfort Grill on Fridays at Turner. And having that kind of holistic college experience, I think, is just as important as hammering down and focusing in on your education as a whole.
I just indicated to Marlene, I want to add on to that and give you guys a little bit of career advice right now. For whatever department you are considering or what engineering degree you're considering, I would recommend that you go on Handshake and find 3 to 4 jobs right now that you would apply for if you had your degree today. Look at those jobs and find out what the skills are, what the attributes are that they are requiring. Between now and graduation, you need to get those on your resume.
Excellent. Thanks, Michelle, for adding that. And we'll just ask the audience, though, how many of you are living in Pritchard right now? And do you still have access to a makerspace in Pritchard? Okay, so definitely take advantage of that. And the second thing is, in all of the emails that I've been sharing with you about Explore Engineering Week, there's a list of resources to help you do major exploration. And one of those things is also a link out to Gobbler Connect. So if you are interested in the Chocolate Milk Club or any other clubs, design teams, please take advantage of that. The link that I sent you automatically filters into any word that says engineering for engineering clubs, but you can take that filter off and you can search for all the 700-800 clubs here at Virginia Tech. So hopefully you take advantage of that. So we have one final question for the panelists. What is your favorite thing about your degree?
Okay, so I'll say 2 things. One would be the size of BME. So my graduating class is gonna be 70 to 80 people. And so with that, I've gotten really close with a lot of people in my major, going to classes like time to hang out with my friends. So I love that part of it. And then also just how hands-on it is. So I've been able to take, as Dr. Reno was talking about during our presentation, everybody takes Cell Lab, which we get to culture cancer cells for an entire semester, run different experiments on them. Bioinstrumentation lab is building circuits, and so our end project was building a medical device. And then right now I'm in senior design, so my team is working with Medtronic to build a spine disc removal surgery device. So we get a lot of hands-on experience and get to really work on real-world problems.
Okay, I was also going to say size, so I'm going to have to shift that a little bit to be more convincing. I would say the community of BSC. I'm on the water side, April is on the biotech side. I would say all professors on the water side I know fairly well. Some on the biotech side, I didn't have as many classes with them. But we do stuff like ice cream socials. Our professional society is having a pizza thing this week. There's a lot of clubs to do. Most of my friends that I have outside of class are from BSC. I've been to my professors' houses for cookouts and potlucks. So yeah, I think when I graduated from high school, which I'm sure you guys are very familiar with, I knew almost everyone in my classes, and I was friends with a lot of them. And when I came to college, I got kind of scared that I was going to get lost in a big sea of people. But within BSC, that hasn't happened. I found my people there. I found professors that I can talk to in the program, and so that's what I would say is my favorite part.
Yeah, I'll also say, yeah, my favorite thing is not feeling like I'm just a number. You guys are in the gigantic chemistry and physics classes right now, and I'm sure that it's easy to feel like you're just a number here, and that, you know, I don't know, not quite as special as like when you really get into a major like ours, and you get to know your professors, and you know all the people in your class, and it just feels more special. You're part of a community that's not even just here in your department, but it's unique across the nation too, so.
Okay, again, I can echo all of that because we have a smaller department. Our faculty are fantastic, but I am going to focus on, there's a fun thing that we do in December. We have a potluck, and we auction off our faculty. So you can come and bid on our faculty and do certain events with them. Last year, I was partnered with one of the faculty, and we went to the escape room. We did that with a group of students. They've done axe throwing, they've gone bowling. One of our faculty had a bonfire in his backyard. So students get the opportunity to bid on and win one of our faculty members, and you can do whatever with them in an afternoon.
Okay, so I have two things. The first one is mechanical engineering is definitely a much larger major, but I actually kind of like that because for some reason, mechanical engineers, in my experience, are like the chillest, funniest people ever, and wherever you go, you're gonna find them in whatever company you're at, and you kind of just get an automatic bond with whatever other mechanical engineers are in the room, and they're everywhere. So you kind of like get a community all around the world wherever you go, which is nice. But also, I think the practical skills that you get from this major are really awesome. I know college is a time where you suddenly have to go from being a teenager to being like a full adult, and there's a lot of adult things you have to know, like home ownership and like buying a new car. And so for mechanical engineers, like I know last year I figured out that my HVAC system had a coolant leak, and that's why my house wasn't heating properly. And I only knew that because I learned how like the refrigeration loops worked in my classes. And things like if your car engine is making a knocking noise, like what that might be from, or why different car engines need different like octane levels in their fuel. So you just learn a lot of practical things that come up in your life all the time. I know I learn things in my classes, and then the next week I'll see it in real life, and I'll be like, oh, like I understand that. I know why that happens. So I think that's a really cool thing about mechanical engineering.
Yeah, one thing I want to add, I also agree. I think mechanical engineering as a whole is you'll have a lot more people. It'll be a lot more broad. But again, I think that's definitely a positive thing. Being able to take, like just to go over some of the courses in the major, you'll be taking a statics course, which I know if you're on the aerospace track, it's called Statics and Structures, which focuses a lot more on like aerospace applications. And then mechanical engineers will take deforms and like aerospace is one of the more comparable majors to mechanical engineering. They'll take a thin-walled structures class, which is like very much more focused on rocket design and the structure that is involved with that, which is really cool if that's what you're looking to do. But as a mechanical engineer, my deforms and dynamics class as a whole was more broad, and in my opinion, way more applicable, which is something that I really like because, like Hannah was saying, I can kind of look to things in real life and see how what I've learned in my classes is applicable to that. And I think it's really valuable to mechanical engineering as a whole.
Excellent. Thank you all so much, and please give our panelists a round of applause. Thank you all. So you're free to leave the stage so they don't blind you with the projector. So there's a few general announcements for you tonight. The first is that I have some College of Engineering stickers at all the tables when you leave. So we do have each of our programs that were here tonight, we're going to also give them a few minutes to go back to their tables. So if you have some specific questions you want to ask of one of the ambassadors or the students or the faculty that were here, they're going to make their way back now to the tables. So feel free to stop by, ask them questions. And then make sure you pick up a free sticker. If I run out, there's a whole box at the back of the auditorium area. We can make sure that you get one of those College of Engineering stickers. And as far as the class assignment, we'll get the screen loaded, and then you'll be able to make sure you use the QR code, completely fill out the questionnaire, and definitely take a look at the tables at the back as you're exiting. Thank you all so much for being here tonight. I will see you tomorrow. Thank you.